So the circle is basically x squared plus y squared equals r squared, which is Pythagoras' theorem, because we know that if we have x, y, r, it forms a right triangle, and we get that Pythagorean relationship. So the rectangular hyperbola is going to be this shape here. So as we cut through the cone straight up and down, we're going to generate these curves, these green ones here. Okay, and they have asymptotes that go along here. These asymptotes are actually the generators of the cone. So if you can imagine that, those are the cone parts, okay, that it doesn't touch. So these are the curves that form, and we're going to end up with a formula x squared minus y squared equals plus minus a squared. And like I said before, the rectangular hyperbola actually is if you were to actually rename it, probably should rename it the square hyperbola, because like the circle, it's symmetrical. The rectangular hyperbola is the symmetrical version of the hyperbola. There are other hyperbolas that are kind of elongated, and those are just called hyperbolas. Okay, and one of the things that I like to visualize with these hyperbolas is there's actually this kind of square that generates the asymptotes. Okay, so there's this kind of square here which just touches the vertices, okay, and where the asymptotes actually can be drawn through the diagonals of that square. And this square shape is kind of analogous to this circular shape. It is the vertically and horizontally proportional version of the rectangular of the hyperbola. And this is a rectangular hyperbola. Okay, so there's other hyperbolas that actually have different shaped squares or rectangles like this, and their asymptotes will go more like this. And their hyperbolas tend to be more elongated in this way. Okay, so the rectangular hyperbola again is more like a square hyperbola, and it is related to the circle, just like circles to ellipses, rectangular hyperbolas to hyperbolas. So the circle is generated from the distance formula or the radius formula, which is just using Pythagoras. Okay. So the hyperbola, how do I determine what the hyperbola looks like based on the equation? So I gave you the equation here. It's x squared plus y squared equals plus minus a squared. Well, here I have plus a squared, and that a must be equal to 3. So that's one thing maybe I should make a note of. Okay, the a value here, since this is a squared, the a value must be equal to 3. What is that 3 going to be? Well, that 3 really is similar to the radius. Okay? And it actually allows us to figure out what this graph looks like. So if I think of the domain and range of this, so let's just look at the domain. Okay, so what can x equal? X squared equals 9 plus y squared. Now, x squared can be any value, but there are some values it can't get to. So the smallest that y squared can possibly be is going to be 0. Well, that makes the smallest that x squared can be, it has to be 9. In fact, we can make this restriction. X squared must be always bigger than or equal to 9, which then makes a restriction on x. Well, x can be at biggest 3, okay, so it has to be at least 3. Okay, it can't be any smaller than 3, and it can't be any bigger than negative 3. So then we've now established a domain for this. Okay, so this ends up being the domain. Now, if we did the same for the range of this, well, notice that there's a gap here. If there's a domain restriction on a hyperbola, it looks like the y's go infinitely up and infinitely down. Well, let's just check this. Is this really the case? So let's solve for y. So y, this is going to be for my range. I'm just going to test my y. So the y squared is equal to, it's going to be x squared minus 9. Well, that means that the y can be 0. Okay, the y squared can be 0, because we can make this into 0. Okay, so this is equal to. So y could be 0, and y can be any numbers bigger than 0. Well, if y squared is that, so basically that also makes y, okay, and maybe I'm going to write that down, y squared must be greater than or equal to 0. Well, if y squared is greater than or equal to 0, then y must be bigger than 0, and it also must be less than 0, because the negatives can be also, when they square it, they're going to be bigger than 0. So in this case, we end up with y is all real numbers for my range. Okay, so that ends up being my range of this function. And I kind of did this algebraically, but I didn't really have to. I could have kind of understood it, what the graph looks like. In fact, notice that if my radius squared is 9, my radius is 3. If a squared is 9, my a is 3. And notice that the a actually represents the domain restriction. So when I actually graph this function, it looks like this. Okay, it has to be at least 3, and it goes on this side like that. Okay, so I have an infinite range up and down. And it also has a domain restriction at -3, and it's got to go this way, up this way, and down this way. Okay, so this actually represents, that a value actually represents the radius value. Okay, it is just like a radius. It's the distance from the center. In fact, because it's a rectangular hyperbola or a square hyperbola, that a value generates the square like this, and that also will generate my asymptotes. Okay, so this is actually 3 in the vertical, -3 in the vertical here, and it generates our asymptotes like this. And so we end up with this graph. If I actually solve for y like this, my y equals, maybe I'm just gonna, I think I may be missing a step here. So if I solve this equation here for y, I get square root x squared minus 9 and plus minus. As x gets really, really big, this negative -9 doesn't really affect it very much. So we end up with like 10 billion squared minus 9 square rooted. Well, that's pretty much 10 billion. Okay, so we end up getting this. We end up basically getting this equaling y equals plus minus x. Square root of x squared is x, and that ends up generating my asymptotes. Okay, so those are my asymptotes here. Maybe I'm going to highlight that. Okay, so y equals plus minus x. Those represent these diagonal asymptotes, which can be generated from this square that I've built in here using my a, or my hyperbolic radius.